Okay, I will send it to you through the group. Actually, I'll do that now before we even start, so that you can download it. So here it is. Okay, so I'm sending it to the Google group. So hopefully you have access and you can download it straight away and save it in your directory. And in the meantime, I will get started on the screen sharing. Okay, so so this is my folder for the course, and okay, I'm gonna go ahead. So this is from the last session, and yeah, we didn't have time to go through a practical example. We kind of explained the theory behind regression and all, but didn't have time to actually practice and kind of like look at the steps that you will usually go through when you do a regression, or when you analyze your data. So yeah, Aliana, you should get it. Okay, cool. So you got the data set. So just feel free to download it so that, you know, if you want to work together through it, then you will actually look at the same values. Do you both work on snow leopards by any chance? I mean, yeah? No? Okay. Aliana, can you unmute yourself and just tell me actually what you do with snow leopards in general? It'd be interesting to know, if you don't mind.
Yeah, so I'm still a student. So I'm a master's student at Beijing Forestry University.
All right. Do
yeah.
Do you have a project for?
Yeah, so specifically my project, I am hoping to look at snow leopard and other carnivores in the area and their diseases.
Okay.
But I do help with other projects in my group that do, you know, like counts and occupancy and all of that kind of stuff, monitoring and such.
Okay, so actually, if you look at disease, like, do you actually potentially work with parasites, and do you know anything about ticks on snow leopards, since that's what we're going to be doing today?
Yeah, so the parasites I'm looking at though are intestinal. I don't look at ticks, but
yeah, okay. Okay, right. So I simply, I came up, with this idea to make a ticks data set. And we'll see, we'll see how to kind of go around analyzing it. It may not be realistic, the numbers that I came up with, because I have no idea, but I'm assuming snow leopards get ticks sometimes, depending on where they live. But so yeah, let's just go ahead. So I'm gonna make a new script for this course. And let's, I'm just gonna give it a name so that if I come back to it, I will know what we're talking about. So this is the first session, the 5th session on the 1st of July. 5th of July. I'm just gonna copy and paste this here. So again, loading the same data set, right? So if I run this line, it should recognize that I am, because I'm in the correct directory. So make sure the working directory matches where you expect your file to be. So I'm looking for uncia.csv as always. And I'm just going to import the second data set for ticks. It will be essentially the same code as this, reading the CSV, because it's a CSV file. But this time it's not called uncia, it's called ticks. There we go. So now we see that in our environment, we have 2 data sets now. If I want to inspect the data set, so again, it's very good practice to annotate your script, because if you come back to it in 6 months, it is nice to have some idea of what you do at every step, because you can easily come up with very complicated code, which at the time makes sense for because you're kind of working on it as you go, of course. But once you get back to it 6 months later, you may not understand what you did. And that's problematic because if you want to work on the same data, you don't want to make any mistakes. And that's why annotating is absolutely crucial. And it's a great habit to take if you don't already have that. Okay, so inspect data. That should be, of course, pretty self-explanatory from the code. What I like to use is the head function. So if I run this, remember you can do, if you simply go on the line and do Control Enter, that the line will run, or you could click Run instead, and that particular line where you're at will run as well. If you want only specific sections of the code to run, then you can highlight what you want to run and then again click Run or do Control Enter. That's the same thing. So head gives me the first 6 rows. If it's a data frame, it will give me the first 6 rows. So I see, okay, I have this X variable here, location, the gender, the sex of each animal, their length, and weight. I'm gonna go, so yeah, the reason I want to look at these data sets is because they're separate right now, right? I do know that I have 110 rows, 110 observations in each of them. So hopefully they should match, right? It should be one value of ticks, one count of ticks for each animal. The only thing that I did, and this is simply to practice, I kind of scrambled the rows. Just think of this X variable here as the ID of your animal, okay? But they are scrambled. So the question is, how are we going to put these 2 data sets in a single one so we can then work on it? So this is just to kind of get familiar with base R again, to like some basic functions. And let's say you're collecting blood samples from animals and you send them to a lab and they give you a data sheet. Hopefully you have an ID for each sample so you know which one is which. So if you bring back the data set and you import it and you want to kind of put all of your data together, you should be able to know how to match these data sets. That's what we're going to do here. Of course, if you collect all your data at once in the field, actually, if you're counting ticks, probably you will have this, all your data in one place from the beginning. But let's assume you did not, and let's match them. Right. With ticks, I also get the location and I also get the sex of the animal. So that's actually some information. If I want to double check if I match properly, if I end up with counts from a leopard from Altai on the same row as a leopard that is actually from Wakan, I know that I mismatched my data sets. Okay, here is pretty easy because the ID is just from 1 to 110. So if I simply sort the data frame by the X variable, I should be able to recover the correct order, right? So let's try to do that. So I'm gonna sort the tick data set by ID in increasing order. What I like to do though, first is check whether the UNCIA dataset is also ordered. So if I check just UNCIA X, so I check so this will return a single vector, a vector of numbers. So simply that entire column of that dataset. So let's run this, and I see that yes, I do have everything ordered. Okay, you can check one by one if you want, but yeah, everything should match. So I don't need this. This was really just to check. I want to reorder ticks, so I will reorder the entire data frame. So ticks is a data frame, right? With 110 observations and 4 columns. So I'm gonna reorder it, and to do this, I can't use the sort function here because sorting will only sort a single vector. I will use the order. So of course, what I want is the entire data frame again, which is why I simply put ticks. And then I'm going to use the square brackets to reorder the the rows. So remember, in the square brackets for a data frame, we need two indices. We need the rows here, and the second one is always the columns. So it goes rows and then columns. To give you an example, if I want row number 1 and column, let's say 2 to 4, which should work because I do have 4 columns. I don't want to overwrite ticks at this point, so I'll simply highlight ticks, like this bit of code, to see what it returns. And I get the first column, which is here, plus column 2 to 4, 2, 3, and 4. And this is what it returns. Let's say I want rows number 1 and 3 and then 2, it will also work. It will actually put them in that particular order: row 1, then 3, then 2. This is what happens, and I can even check with this is the head of the data frame, and I see that the first one here is row number 1, then row number 3, and then row number 2. So it reorders like this based on the numbers that I put. Of course, I don't want to do this manually. I want to do this automatically. So I want to extract first the order. I'll just create an object called, I'll call it order ticks. I don't know. Let's just go with that. So I'm going to create an object here. And that object will be order. So order is a function, and I want ticks. So this is my data frame that is ticks, and I want to look at the first column, right? The column called ticks specifically, and it will tell me in which order the values are from low to high. Okay, so if I run if I run the whole line, I see that I created an object. It's a vector of 110 numbers. And if I look at it, I'll just do that in the console. I get 1, 17, 19, 23, 27. What this tells me is that the lowest number of, oh, sorry, it's not ticks that I want. It's X, sorry, my bad. So I'll just overwrite it and I'll get a different set of values now. And I will re-look at order ticks. So I get these numbers. It tells me that the lowest number in the X column, which is my ID column, is row number 91. So if this is correct, then the value for X for that row number 91, it should be 1, right? Because it goes from 1 to 110. Let's just check it. So if I look at row number 91, and I want to look at all the columns this time, so I'm not putting anything in the column index here. So I'll leave it blank. And I see that, yes, indeed, for row number 91, it is the first one. It is X is 1. So that is the order that I want. So what I can do is simply put here order ticks. So that object, it tells me which order it should be. So which row to put first, which one to put second. So it tells me, okay, put first the row number 91, then 28, then 29, and so on. So it will reorder based on that column. So what I just did here by running this line is I overrode ticks. So if I look at the first cases, now it should be in the right order. And we can see indeed that it is 1, 2, 3, 4, 5, 6 in the correct order. Okay, so this was simply just a little bit more practice on how to use base R and how to reorder data frames. I'm now going to combine ticks, tick count. Right. I'm going to add the tick count to Uncia, which is our main data frame. So I'm going to create a new column in Uncia that I'm going to call ticks. Okay, and this I'm gonna take a vector of numbers, which will be the tick counts. And I can find this in the data frame that is called ticks, in the column called ticks. And because I already reordered the data frame, so that I know that they will match, I know that I will put the right value for the right leopard, basically. If I want to be sure that I didn't make a mistake, I could actually also import the X value. So I can put ticks, and then I could import two columns. The first one, so the X column, and the one called ticks. So this will also work. But here I'm saying, okay, I want both columns from the ticks data set. And I don't want this to put, because this will create a single column. I can't put two columns into one. So I need to create two extra columns that I'm going to call X1 and ticks. Okay. So this X will become X1 and ticks will be ticks. If I run this, and now if I look at Uncia again, I can use this line. Then I've created these two new columns. The reason I'm putting X1 is that, okay, if I have any down, I can actually check whether X and X1 match, because if they don't match, then that means I have a tick count for a leopard that is from a different leopard. So I'm kind of mismatching. I can look at the entire data frame also, not just the head, to make sure it does match. So so here, this is my X column. I see that, yeah, even on that row, number 70, it matches, 92, it matches, 101 matches too, up until 110. So I know, okay, at this point, I know that I'm not making any mistakes. I do have the correct tick count for the correct leopard. Okay, so now we've done this. I think I'll just remove that column as well. So I'm going to overwrite Uncia again, and this time I'm going to remove the X1 column because I don't need the X twice. And I'll just give all the column names that I want. I want X. I want location. I want sex. I want length, weight, and I want ticks. So basically all the columns apart from X1. If I run this, you'll notice what happens to Uncia here. It has 7 variables. It should become 6 because I'm removing a column. And there we go. So we're happy for now. And the last thing still from this code actually is I still want to convert. Well, let's do. If I run a structure of Uncia now, this is what I get. So X is an integer. Location and sex are character columns because they have strings of text in them. Length is an integer, weight is an integer, and ticks is also an integer. I would like to have these as factor, not character, preferably, so that it becomes easier to work on. I'll show you why. Because if I took summary Uncia, this is something we've done before, but you see, it doesn't tell me much information for these two columns, location and sex. It just tells me, okay, it has 110 and it's class character with very little information. Whereas here, for the other columns, it does give me a summary. It gives me the median, the mean, and so on. So, which is an informative summary for numbers, right? But I'd like to have some informative, something more informative for these categories as well. So if I convert these two, I'm just taking the code from the previous session because that's something we had done already. If I convert location and sex to factor, So Untia location becomes, it's Untia location, but as a factor. And we do the same for sex. It simply overwrites each of these columns with a factor instead, a vector that is a factor, not just a character. So I run this, and I check the structure again of the data frame, and I say, okay, now I do have factors with 2 levels. So it does recognize that there's 2 kinds of character strings in a sense, like 2 categories. Before, as character, it didn't even care whether some were the same or not, whether they were actual categories. If I look at the summary now, I have something a bit more informative. Is that it tells me, okay, location, there's the location outside, the location backhand, and it gives me a count for each of these. So I know I have 41 leopards from outside, 69 from backhand, and it also tells me the same for the sex. Next step is, again, similar. So these are just the same steps as before. I wanted to remove my outliers. Remember the fat dwarves, and I do have one NA here in weight. I'd like to remove this NA value because I want to work with both of these. So same thing, I'm going to copy and paste from session 4. So you can do the same, open the script from the session 4. And, you can simply copy and paste these lines. So this will subset and keep only leopards that are above 60 centimeter in length. And this will subset, it will only keep the complete cases, meaning any row that has an NA, it will remove it. So I will run this and that. And we see that now Untia has only 103 observations. So we removed 7 leopards from this by doing that. Okay, remember we had these 2 methods for BCI. One was simply dividing the mass of each leopard by its length, and that's just, it gives you a number, and that is one way of calculating a body condition index. Another one is to do the same, but taking the log of weight and the log of length instead. Let's do that. So again, copying and pasting. So now I'm adding columns to my data frame. If I look at the head Untia, I see now that I have a column called BCI1 and another called BCI2. If you remember from last time, these 2 measures of BCI are very, very highly correlated. So they give you kind of the same information. All right, so now the first step of analyzing the data. Something that is absolutely crucial that a lot of people sometimes skip or don't spend enough time doing. Today, we won't spend much time doing it because it's only for the purpose of demonstrating what we can do. It's data exploration. So looking at your data, knowing what it looks like, knowing how different variables are related to one another. So data exploration. The first thing I'm going to do is I'm going to build a histogram for each of my numeric variables. I'm going to focus on BCI2 here, not the first method, only the second one. So maybe I want a histogram for length. Okay, sorry. It doesn't. So here I'm getting an error message because R tells me I can't find this object called length.cm because the way it's written here is that it seems like I have a vector of numbers called length.cm. That's not the case. What I want is the column. It's a column from the Untia dataset. That itself is a vector of numbers, so then it will not give me an error. So, okay, I have this histogram, which kind of suggests that, okay, it's normally distributed. The mean is around there, I think 105 or something. I'll do the same for weight. Okay, so I get a similar picture, and I'll just copy and paste and do the same for the BCI2 column. Again, something that looks normally distributed. It seems to be going up to 0.8 and minimum 0.65, more or less. it would be good to know how they are. Oh yeah, I will do the same now for ticks. And this is a very different kind of distribution here. It's a number, so it goes from 0 to something else to, well, here up to 14 if you use the updated ticks data set that we have. Are you following with the coding? Do you manage to code at the same time as we do this? Okay, perfect. Just to check I'm not going too fast. Okay, so this is simply because, okay, we looked a lot at normally distributed data throughout this course. This is count data, and count data follows a different kind of distribution that we call a Poisson process or Poisson distribution. I'm sure you've heard of this before in your class. A Poisson distribution has only one parameter called lambda, I think. Unlike a normal distribution, which for a normal distribution, if you remember, to be able to draw that curve, we need to know the mean to know where the curve should be centered, and we need to know the standard deviation or the variance, because we need to know how flat this curve is, like how is the data spread out. If you know both of these parameters, you should be able to draw your curve of your normal distribution. With a count data like this, what happens is that smaller values are very common. So it's very likely that you have maybe 0 ticks or 1 tick. And the more ticks, in this case, it becomes less and less likely. This is what this distribution tells you. And we can see that. We can see that from 0 to 2 ticks is many leopards. And then, the more you have, the less likely it is. Right. So you can think of other kinds of data that are distributed in this way. So if you count leopards, it will be the same kind of process. If you do transects and you want to, you do a road transect and you count leopards on the side of the road, it should follow a similar Poisson process. Okay, which are usually the case for count data. So count data, appreciate that it is very specific. It is going to be whole numbers, it's not a continuous variable. And it doesn't go in the negative, of course. Also, so sometimes if you look at temperature, for example, it can go in the negative. We looked at length and we looked at weight before, which of course also cannot be less than 0. And with number of ticks, of course, it's the same. It cannot go below 0. All right, so I'm just going to call this section here inspect numeric variables. So these are all our numeric variables. What about, okay, so the main question we're going to have with this exercise oops. We are going to be comparing tick number between locations. Okay, so I don't know what our main research question might be for this exercise, but we can decide. If, let's say, this was like a conservation kind of project, and we are interested in knowing if, we might be interested in knowing if the leopards from one location are maybe in better body condition than the other. And if we look at the number of parasites that they have, this might give you an indication on their health status, and maybe this has conservation implications. So I guess this will be our main question here, is to look at the number of ticks on leopards. And we want to know what makes a leopard have more ticks or not. What factors are involved. Maybe the body size, maybe its body condition. Maybe if it has a worse body condition, it will have more ticks, or maybe the other way around. And of course, maybe our 2 different locations have leopards with different number of ticks. So we'll just look at that and see what we can make from this. Okay, to look at these numeric variables by location or by gender, for example, if we want to control for sex, we'll have to use box plots. So a box plot uses, we can use the formula for this, the formula notation, meaning our response on, so the y-axis will be our numeric variable. We're going to use then the tilde here. And the x variable, of course, will be our category. So we have box plots for different categories. The first one will be location. And here, of course, again, R will look for objects unless we specify a data frame. So if we specify that the data is uncia, then R will find length and location, these columns. This is what we get. So length, we know that lepers and Vacan are a little bit bigger. And if we do that for each variable, so I'm going to do that for weight, we're going to do that for BCI2, and we're going to do that for, for ticks. Of course, that's the main variable that we're interested in. So weight is as similar as length, which makes sense. Bigger leopards should also be heavier. So we have a similar distribution here. Wakan seem to have leopards are a bit heavier on average. ECI2, okay, we do have, based on our measure of body condition, it seems that leopards and Vacan are in better body condition, and what we're mostly interested in is tick number. And here we seem to, it seems, and we'll check this, there's obviously overlap, but maybe on average it seems like leopards in Vacan have a bit more ticks than the ones in Altai. So this is the first indication of what the data looks like. Remember, another really interesting way to look at how variables are related to one another is to look at their correlation coefficients. We can calculate these, or we can plot the data. So we can plot different numeric variables against each other. So look at correlation coefficient, correlation between numeric variables. I like to use this package here called ggalley. You won't be able to run this line if you haven't installed it before. Just to remind you, install packages. This is from the CRAN library. So if you just run this, R will find it. It will connect to the CRAN library and download this package. Once you downloaded it, you should, in this tab, packages tab, you should be able to see it. So this is taking a bit of time. Okay, while this runs, I will simply load the package. So once you install the package, then you can load it. And to load it, you type library and ggalley. Okay, so here is my list of packages, all the ones that I've installed before. So this list that I have here will probably differ from the one you have. And if I scroll down to ggalley, I see that it's there, and I see that it's ticked because I loaded it. If you don't load it, then it will be there still because you've installed it, but it won't be loaded. ggplot2 is also loaded because ggalley, it's an extension of ggplot. It uses ggplot to work. If you're not familiar with ggplot, this is a very common package to use to plot graphs. It makes really, well, graphs that I think are much nicer than the base graphs, at least. And I guess a lot of people are also of this opinion. So that's why both are loaded here, because by loading ggalley, I'm loading ggplot at the same time. And then this function called ggpairs, which allows me to look at a number of continuous variables, of numeric variables, or in my data set. So the ones that I'm interested in are length. There is also, oops. And there's weight, kg. Of course, here the names should really match what you have as column names, otherwise it will not work. Can of course unfold this to know my columns are here. I want to look at BCI2, and I want to look, of course, at ticks. So this may take a little bit of time to run depending on your computer. And this is these are the graphs that I get. So remember, what I have is I have correlation coefficients actually between all the variables. So between weight and length, for example, I can see that they are really highly correlated. For each variable, this is why I like this function. It tells me also how it's distributed with the density function, with a density curve. It's similar to the histogram, it's just smoothed out. And the area under that curve is 1. That is what the density plot does. So I can see it that these seem to be quite approximately normally distributed. Ticks, again, is not, because we have Poisson distribution. And we can see how correlated they are by plotting them against one another. So BCI2, we realize that measure of body condition is highly correlated with weight and with length, which makes sense, but at the same time, I'm not sure if that's what we desire, because that means that leopards are bigger will be, by this measure, we'll say that, oh, they are in better body condition, which might not be what we want, because by incident with this, it will tell us, for example, that females who are a bit smaller in body size, it will tell us that they are also in worse body condition, which may not be accurate. So I don't know if we want to use that measure of BCI. We'll actually get back to it. We're actually going to use a different measure in a second. The other thing we can notice here is that maybe we do have a slight increase in ticks with length and with weight, and of course with BCI. But because all of these are really highly correlated, that's not surprising. But in general, then what this tells us is that it may be there is some slight correlation between tick number and some other measure. The correlation coefficient does tell us that there is a slight increase. The Poisson correlation coefficient is 0.2 here, 0.28 here, and nearly 0.3. It tells us that it's significantly different from 0, so there does seem to be some correlation, but quite weak. If you drew a straight line through these cloud of points, of course, there's a lot of error around it, which is why here the error is much less, because all the points are way more aligned. Remember that if they are perfectly aligned, then you'll get a correlation coefficient of 1. And here, BCI2 and weight, for example, are very highly correlated. So there's a concept we talked about last time called residuals, which is a very important concept when you do a regression. We're going to explore this concept a bit more in our calculation of body condition, using a different method again. So we're going to call this method 3, or BCI method 3. So here so in this little part of code, I'm going to calculate BCI again, but using a different method. I'm going to use the residuals of log weight versus log length. The reason I'm using log is because there is not actually a one-on-one increase between weight and length, meaning that the bigger you get as a leopard, the more mass you'll get. And if you get 10 centimeters, you won't get a fixed increase in weight. Once you're really big, that extra centimeter of length you'll get will correspond to an even bigger increase in weight versus, compared to if you are a smaller leopard. Sorry, that was not really clear, but yeah, that is why we're using the log. So that the relationship between log and weight, like log weight and log length, is more linear. It's more of a straight line rather than a curve. Actually, weight against length itself is not going to be a straight line exactly. It's going to be a bit curved. You can actually see it there. Weight versus length. Well, it does seem quite like a straight line actually, but there is actually a bit of a curve in here. It goes kind of like upwards a little bit. by taking the log of length and the log of weight, that relationship becomes more of a straight line. That is what we're using in this. So I want to get back to plotting the weight versus the length. Oh, actually, the log of weight versus the log of length. Oops. Oops. Length. Okay, so now I'm plotting this to show you what it looks like. And if I drew a line of best fit through this cloud of points, and I could do that, remember, we can, from the previous session, we can calculate the slope and the intercept. And if we did that, we could draw this line of best fit. What the line of best fit will tell me is what is the average increase in log length for an increase in log weight. Actually, sorry, I want length on the x-axis and weight on the y-axis. So I'm just going to revert these two. I just inverted the y and the x-axis. So for every increase in length, there's going to be an average increase in weight, which will be represented by this line of best fit. It's the average increase between the average relationship between the two variables. And the way we're going to calculate BCI here is by taking the residuals. So what this will tell me is that if, so for let's say, take a leopard that is 4 points, well, this is the log, so that's what the values are a bit strange, but the log of 4.6, so the log of length, which is 4.6, for that particular leopard, there is an expected value of weight, right? We can see that it kind of ranges in this region here. It can go from here to about here, right? We won't expect a leopard of that particular size to be that heavy because it would need to be bigger in size to be able to reach that weight. And similarly, it shouldn't be, for that particular size, it can't be below a certain weight, right? Otherwise, maybe it'd be dead. They just don't exist, these leopards that are so light in weight for a particular size. So it will range, it will be within this range. And there is an average value that you would expect, right? You could calculate the mean weight, the average weight for that particular length. So if you will, and there'll be so error around that expectation. Leopards might be a bit heavier than you would expect for that particular length, and they might also be a bit skinnier than you would expect. And this will be our measure of BCI here. If it's above the line, then it is heavier than you would expect. Which would translate to, oh, it's in better body condition. And similarly, if it's actually less heavy than you would expect, then you could say, okay, that leopard obviously is quite skinny. You could say, okay, it's in worse body condition compared to the average. So that is one way of measuring body condition. And this is the one we'll use because with that particular measure, I would not expect the BCI to be correlated with body weight. It will be around the line. So how are we going to do this? Okay. For this, we're going to build a linear model, actually, because we want to calculate this line of best fit, right? And one way to extract it, so remember from the side, we could calculate it. We could calculate this line, and we could work out what is our expected value for each particular size, our expected weight for each particular size, and then simply calculate the difference, and that would be our BCI. We will extract these values by using a linear model because the LM function will return you these values as well. So to do this, I'm going to create an object called mod. And mod will be a linear model between, so we said between log of uncia weight tilde. So this is our y variable, and the x variable, which is on the right hand side, will be the log of UMSIA length. Okay. Just make sure I'm getting this right. And will this work? No, sorry, it doesn't work because I will put weight here. Oh yeah, I didn't close the bracket, that's why. So actually, sorry, I will remove the UMSIA here because I will actually simply put data here equals UMSIA. So here, R will look for the columns from the UMSIA data set called length and weight, and it will log it. So I can put the log function here. And if I do summary, oops, of mod, my fitted object, my regression, it will give me the coefficients. It will tell me that the intercept for that line is minus 3.5. So when length is 0, the log of length is 0, the log of weight is minus 3.5, and so on. The slope is given here. So for an average, sorry, weight and length. Yes. So for every time the log of weight increases by 1, the log of length increases by 1. Sorry, no. Every time the log of length increases by 1, the log of weight increases by 1.4. And I have standard error, so I can even calculate the confidence interval there. Okay. So I'm just going to go ahead and add that line. So I already have a plot here, and with the line function, this will simply add a line, which actually, if I want to add a slope, I need to add it's called add line. The intercept, I need to remind myself how to use this function. So with the question mark, right. So A and B here, so I could put different arguments in here. A and B will be the intercept and the slope. So my intercept would be A. And I can just take the value from my regression here. The intercept I know should be that. And the slope should be this. And I'm going to put a color. The default will be a black line, but I want it to be blue so we can see it. And if I run this, you see that it adds the line of best fit here. This is basically my regression. It's a simple regression between two variables. It gives me a slope and intercept, so I can go ahead and plot that line. Remember, I could have calculated these values using the equations that you have on the slides of session 4. Okay, it seems to fit. This is the line of best fit. It minimizes the sum of squares, the error. Now what I can do is calculate for every length, for each of my leopard, I can calculate the expected value and how much it differs from this. And this will be my value of BCI3. So let's do this. UNSIA BCI3 now is going to be, actually, first I'm going to create an object to make my life a bit easier. Expected. So I'm going to call something called weight expected or expected weight, I guess. So I'm simply going to calculate, so for every length, what is my expected weight of the leopard? Or in this case, I want to use the log weight. So I'm going to do it like this. I'm going to create a column actually here called log weight. And I'm going to create another column. Oops. So it's a bit messy. Log length. So I'm going to use log length and log weight because in my equation here, in my regression, I'm using the log of weight and the log of length. So log of weight of length will be log of Unsia length. I'll go ahead and plot this, and this is the same, except that this is weight. Okay, so now I added columns to Unsia. They are here. These values are the same that are plotted on this graph, of course. And what I'm going to do is, so for every length, I have an expected value of weight. This is basically the blue line here. This is what I did with my regression. So if I calculate it, log weight x, so expected log weight, I will simply go ahead and plug in the equation here. So remember our formula for linear regression is going to be the y equals a plus beta x, a being the intercept and bit like alpha is the intercept. So let's go with this. It's I'll just put it here. Y equals a plus beta x. This is a very simple linear regression with between two variables. Variable x, which in this case is log of length, y is log of weight, a is the intercept, and this is the slope. So if I simply input these values here and there for the intercept and the slope, I would have my corresponding value for what I would expect the weight to be, the log of weight to be for a particular log of length. So this here is my y. It's here. The intercept is a, so I'll just put that, plus the slope b times Unsia log of length, right? Okay, so if I run this, I'm adding an extra column to Unsia, log of weight, and I can compare them also. So if I call okay, which columns are these? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So column 10 and 11 are my actual values of log weight and my expected values. So if I call these 10, so this will return these two columns. This is what I get. So I get all these values. And I can see, okay, for example, my first leopard here, the actual log of weight is 3.4, but the expected value was 3.43. So it is slightly less than what I would expect on average, meaning its body condition will be negative. The residuals are negative because they will be this minus that. And we can do this for each leopard and see which ones are in better body conditions than others. So this one, for example, has a log weight higher than you would expect. So this particular one, number 4, has a higher body condition. Okay, so we're finally getting to the part where we are calculating the BCI. We simply need to do Unsia weight minus what you would expect, which is that pretty column. So if I run this, if I now call the last 3 columns, so my last 3 columns are the log weight, the expected log of weight, and the BCI. So the BCI is simply this minus that. And this is what I get. I get some negative values, some positive values. And the further you are from the curve, if you are very far below, you have a very bad body condition. If you're very far above, you have a very good body condition, if you will. Okay, so sorry, that took a bit of time. We are already an hour in and we have still not done our regression. Let's carry on. I'm just going to now rerun this. I want to check now the pairs, like how, so here, I'm going to check correlation between my numeric variables. But this time with BCI3, my new measure of BCI. And let's see what we get. Okay, so remember how BCI2 was very correlated to the length and the weight of leopards. And now we end up with some kind of a cloud of points. It's not even, sorry, is it correlated? It is still significantly correlated with weight, not as much as before. It's no longer a one-on-one relationship, like nearly a one-on-one relationship. We can see that from the cloud of points. It's very spread out, but there's still a kind of a slight increase. The bigger you are, the better your body condition on average, which makes sense. Actually, we do want that because, you know, on average, if you're heavier as a leopard, of course, that depends on your size, but if you are heavier, then you should have a better body condition. But at least now the BCI is no longer correlated with length. This is important because if you want to look at the effect of length and body condition on the number of ticks, then you would rather have these two variables not be strongly correlated. By default, like the golden rule essentially, is that your predictors in a linear regression should not be correlated. They should remember this multicollinearity assumption in the regression. We mentioned that last time, meaning that, yeah, your predictors, if you have several numeric predictors, continuous predictors, to explain your y variable, which in our case will be the number of ticks, they should not be correlated with one another. Why? Because if they are, the estimates for them, for each of them, will be biased. Plus, their individual effects will not be quantified properly. Meaning that if one is significantly influencing number of ticks, but also the other, then their respective effect will be confounded. Meaning that they take on each other's variance to explain number of ticks. Which is why if we were to run the regression, which we're just about to do with BCI2, we would have to probably choose between either BCI2 and length or weight. We can't put them the two together because they are correlated. So they kind of, how do you say? They explain a similar kind of information essentially, because when one increases, the other increases as well. So that's something that's partly why data exploration is such an important step, because you do want to know how your different variables are related to one another. If I didn't do this step of data exploration, I may not have realized that BCI2, that particular method, was strongly correlated with my length, with the length of leopards, and maybe I would have, have them both as predictors in my regression, and so my entire model would not have been very valid. Of course, after running the regression, you should check your model assumptions. We'll do that anyway. So we would have probably realized that as well. But now we know that we have a measure of BCI, which is not correlated with length, which we're going to use actually as an input. BCI also doesn't seem to be very highly correlated with number of ticks. So maybe from just looking at this, we could expect that, okay, maybe body condition of a leopard does not really influence how many ticks they get, at least based on that data set. Okay, so that was step one. Now let's go ahead and do step two, actually fitting a linear model. All right, so how do we do it? So we're going to call this fit one. So the first fit, we're going to have a couple. Okay, so fit one is going to be a linear model. So this is the function lm. Our y variable, so the response variable, is going to be ticks from our data set, explained by a series of predictors. So if it was a simple linear model, we would have only one predictor, whichever we are interested in. But here we want to know the combined effect of different predictors. So the first thing, actually, I'm curious, what do you think we should put as predictors? So we have all these variables: length, weight, body condition. And so what do you think we should, if you know anything about ticks, what do you think could matter to explain how many ticks you have? So you can unmute yourself if you want to discuss this. What do I have in the chat? Okay, so Aliana is saying body condition and the length. Oh, sorry, I didn't see some of the questions. So if I was asking, okay, every time I run a line, it runs but always ends with minus 3.5. Oh. Oh, it's maybe because you just wrote this in the script and you didn't run that. So go in the script, the console of R, and press escape, and it should remove this minus 3.35 or whatever. Okay, so body condition maybe makes sense to have it as a predictor, because yeah, even though we do see from our data exploration that BCI doesn't seem to be very correlated with tick number, we're not controlling for other predictors at this point. So it could still be important, and from a biological point of view, maybe it makes sense. These are parasites, and if you have a better body condition, maybe number of ticks will vary. We could, if we looked at papers before, maybe we'll find that, okay, yeah, with lesser body condition, you end up with more ticks, maybe because although maybe if you have a better condition, in this case, we do see that body condition is kind of correlated with weight, meaning maybe you're a bit fatter and you have more surface area for ticks to attach. There could be a series of factors here to consider. But body condition is going to be one of the predictors. We could think also maybe, okay, a leopard in better body condition maybe will move around a bit more, so it has more chances for, again, ticks to attach, because it will move around grass a lot more than a leopard with less body condition. We could think again already that, okay, maybe actually a leopard with lesser body condition will actually move more, because maybe they want to feed, they want to hunt because they're hungry. Anyway, maybe we don't know in which direction it's going to go, but we do think that body condition may have a role to play there. Why the length? Aliana, why do you think length should be important?
It's kind of like the more surface area. They're longer, they might be larger.
Yeah,
so
that makes sense.
They brush up against bushes more often.
Yeah, exactly. Yeah, I would expect the same. Again, this is just a hypothesis. We have to think about other factors that might drive a similar pattern. Again, maybe a leopard that is higher in body size, maybe is more territorial, and maybe moves around more or less. We don't know. But yeah, just that thought that maybe a bigger leopard offers more chances for a tick to attach. Again, it makes sense to include length as a predictor. What else have we got? There's a body condition, length. We have the sex of every leopard, males and females. Very often, animals of different genders have different behaviors. They may move around differently. Maybe males have a higher home range, or females have a higher home range. In the case of snow leopards, I'm not sure. I have no idea. But we do have that data, and it might be important to control for gender in this case. Okay, so Aliana seems to agree. And we have these two different locations, and I guess this will really depend on our research question. Maybe we are very interested in looking at differences between locations on tick number. Maybe because, I don't know, maybe we want to prioritize our conservation efforts, so we want to know which population is doing better than the other, or There can be a variety of reasons to look into this. Let's just assume that for the purpose of this exercise, that location is something we're interested in looking at. So let's go ahead and put all these predictors. So the first one, I think, was length. We don't need to put weight. Weight is very strongly correlated with length. We already know that. So we can't put both in there. We have to choose one or the other. So we'll choose length in this case because we think size itself is important. It's not the weight per se. Plus BCI3 is slightly correlated with weight, not very strongly, but just a little bit. Just to be clear, linear regression can deal with some correlation between variables. It's not because, if you look at these coefficients and you see, oh, there is a significant correlation between two of them. Looking at, for example, BCI and weight, a correlation of 0.3, okay, it's significant. It's significantly different from 0, but it is not massive. And actually, these correlations between variables, between your predictors, only starts being a problem when it's very high. Like 0.9 would be problematic, which is why we really can't add both weight and length as predictors. They will take on each other's variance if you do that. And your values of estimates will be completely biased. 0.3 should not be problematic. So we could actually include both weight and BCI at the same time. It should not be a big problem. But we already decided to not have weight anyway. So and BCI is not correlated with length. Yeah, it's close to 0 actually. It's not correlated at all. Good. This is kind of what we want. So we'll put BCI and we'll put sex and we'll put location. I think that's all we decided. Of course, we need to specify which data set this comes from, because otherwise I will not find these objects. So that's it. This is our first fit, fit number 1. So this is multiple linear regression. To put OLS, it's an ordinary least square. It's a standard linear regression, nothing it's with the LM function. All right. We need to look at the summary, of course, because otherwise we won't learn anything from this. And this is what we get. What do we get? Wait, something I should point out before we even go further is that we did not put any interactions between our predictors at this point, meaning that if there is, for example, let's say we could put an interaction between length and sex. If we did, remember we would put, so to add this interaction, actually, I could put sex, semicolon, length. And if I add this as a predictor, R will look at whether there is a significant interaction between the variable sex and length. Meaning that if there is a significant influence of length on the number of ticks, so if, let's say, larger leopards are more likely to get ticks, so they have a higher tick count, that relationship will not be the same whether you're male or female. Maybe if you're a male, you are way more likely to get ticks if you're bigger, and maybe if you're female, then okay, maybe you have still a higher chance of getting ticks, but maybe that higher chance is not as much as if you are a male. That's what the interaction does. I did not put any interaction effects interactions in here. I'm keeping the model quite simple. Anyway, so we are really looking at the individual effects. What this tells you, so first of all, remember we have the residuals. So residuals is the same kind of concept that we had when we calculated the BCI, is the error around the curve. So whether it's, so you are kind of expecting a response, so the number of ticks, but you won't be absolutely right. There'll be maybe some animals you would predict had 3 ticks and they end up with actually 4 or 5. That's the error. These are the residuals. And we see that minimum is -3 and the maximum is 11. The median is not too far from 0. Ideally, well, this is one of the assumptions of the linear model, is that the residuals are normally distributed. So the error is so the error around the line of best fit essentially is the same. There should not be more error like above the line than below. That's it. This particular summary here already indicates that there might be some bias here, because the minimum value, the minimum residual is -3. So the maximum should be around +3, right? If you want this to be equally distributed around the expected values. But it's at 11, so it's a lot higher. It's a lot, if you look at the line, there'll be some error way above the line, but not way below. It will be just a little below, like at -3. Yeah. I hope that makes sense. We'll look at the residuals more closely anyway, but this is just a first indication that there is maybe some violation of assumptions here. Then we have our coefficients. This is the intercept. Okay, so the intercept is not something that is usually interpreted. And then we have the estimates for each of our predictors. What these estimates tell you is that if you keep all other predictors constant, and actually specifically at 0, this is the average response you get. So on average, you gain 0.02 ticks for every centimeter of length that you have. That is the estimate that you have. Meaning, on average, there is an increase in number of ticks the bigger you get as a lever. Keeping everything else constant. So regardless of the sex, the gender, of the BCI, if you keep those constant, then this is the average increase. Same for BCI. The bigger, the more the you get an extra 0.3 ticks for every increase in 1 unit of BCI. The sex male here tells you, so this would be the average number of ticks for a female if you keep everything at 0. So length 0, BCI 0, and for the location altai, actually, that is the number of ticks you would expect for a female. It is -0.9, which makes no sense biologically. You can't have less than 0 ticks. But what this tells you is that males on average have 0.3 ticks more than females. And for this categorical predictor here is the same process of thinking, the same thinking process. So the intercept here tells you the number of ticks you would expect at altai, and at vacan you would expect 1 extra tick, 1.6 extra ticks actually, compared to altai, which is quite big, right? That effect. These are our estimates. This is descriptive. This tells you the average increase for each of these variables. Of course, you have a standard error associated with these estimates, and a t-value, and a p-value associated with that t-value. This tells you whether that estimate here is significantly different from 0 or not. And we can see that, for example, we saw, okay, there is an average increase in tick number with length, but that increase is not significantly different from 0. If we were to sample again, we might find actually that this is actually negative, not positive, or it might be 0. So that 0.02 is not significantly different from 0. It could be 0, it could be even a bit less. The point being that p-value tells us that it's not. So we can't say that there is a significant effect of length on number of ticks. But we do see that there is a significant effect of location, that those double stars here tell us that the p-value is less than 0.01, 0.01, yes. So yeah, we can say with confidence here, based on this model, that vacan has more ticks on average than altai. All right. Some other important numbers here are the multiple R squared here, especially the adjusted R squared. The adjusted R squared takes into account how many predictors you have in your model. This is a measure of goodness of fit, the R squared. It tells you how much of the variance your model is explaining, essentially. An R squared of 1 tells you that your model is explaining all of the variance. So all the variability you have in your data is explained. We know why it's there. We have predictors that can account for it. So just based on the predictors you have, if you know length, if you know BCI3, sex, and location, you can know exactly what is the tick number that the leopard should have. You will not make any mistake if you'll know for sure that the leopard has this particular number of ticks. Here, of course, we do not explain all the variation. There is a lot of error. So you might say, okay, based on these predictors, I can predict that the leopard will have 3 ticks, but maybe I'm not very confident with this estimate. Maybe it will be a lot more, a lot less. That R square kind of tells you how good your model is at predicting number of ticks based on these predictors. We need this adjusted R square because by default, the more predictors you have, the better your R square, which is not something you want. It's not, you just want to know whether your model is better or not. But if by default, a model with more predictors is a better model, that's why we need to adjust the R square. That's why the value here is slightly less than the multiple R square, which does not take into account the number of predictors you have. So the adjusted R square here tells us that we explain about 14% of the variance in our data in number of ticks, which is not great. It's a pretty low R square, meaning, okay, our model may not be so great after all. So we're not fitting the data very well. The F statistic is another measure of goodness of fit. It essentially tells you whether there's 2 ways to look at it. You can say the F statistic tells you, does at least one predictor in my model explain the data at least a little bit? If the p-value is less than 0.05, let's say if that's your critical threshold, it will tell you that yes, if it's lower than your alpha level, your significance level, so 0.05 probably, which is the most common threshold, you can say yes, at least one of my predictors is explaining some of the variation and can explain tick numbers in this case. Another way to look at this F statistic is to tell you, is my adjusted R square, so here it's quite low, but is it better than nothing? Like, is it better than 0? So to explain none of the variance, essentially that's what it tells you, is that yes, it's significant. It is significantly different from 0. It does explain some of the variance. In this case, though, it explains very little. Okay, so we get to the next step, which is, step 3. Check model assumptions. One way to look at this is that you can fit a model, of course. You can fit a line through any cloud of points. Whether this is a good, if it's a good prediction, whether your predictors are really explaining your data or not, doesn't matter. Like you can still fit a line through your data points. So yeah, the main question is, is this model valid or not? So remember, there's particular assumptions with linear modeling that I explained that I covered a little bit in the last session, very briefly, because you can really spend an entire course probably on just checking these model assumptions. But the point being, if you violate some important assumptions in linear regression, then you simply cannot trust any of the results you have. So we do have results. We say, okay, well, location vacant seems to have more ticks than the outside location. But if we violated, if our model doesn't fit the data at all, and if we're violating assumptions, then we can't trust these results. We might as well not even have them, right? Which is why checking model assumptions is very important. So together, we'll just check some of them. A lot of the assumptions around linear modeling is to do with the error. the residuals, if you remember. The residuals needs to be normally distributed. They need to be homogeneous also. And this is what we're going to check first. Unlike t-test, for example, the assumption of normality was about the data itself. With linear regression, we're not making that assumption. The assumption is it's also normality, but about the residuals, the error, not about the data itself. This is an important distinction. So you shouldn't, for example, look at, okay, number of ticks, y variable, the response variable, is not normally distributed. That doesn't mean we shouldn't be able to fit a linear model through it. However, just the fact that it's not normally distributed does imply that maybe we'll have some issues, but not necessarily. We can only make that conclusion after looking at the residuals themselves. So let's do that. If I can extract the residuals from the model fit. So by looking at, actually, if I look at the structure, so this will be inspect residuals. If I look at the structure of my fitted object, I can know what it looks like. These are, I mean, it's a very complicated object. It has 13 things, and which are subdivided into other things. Sorry, that's terrible terminology. I have my coefficients. The coefficients are the same one that I find in the summary that I have here. Where we'll see minus 0.89 is here, and so on. And we have the residuals and all kinds of information that we might want to know about our model. What we're interested in right now is the residual error. Like, how much error does it make? So it's going to make predictions. So it's kind of like, okay, we have number of ticks. We know the actual answer for our leopards. We have a model. We know length. We know BCI. We know sex and location. Can we estimate how many ticks that leopard is expected to have? And how much error do we make around that estimate? So let's say we take, leopard number 12, in our data frame. Let's actually look at it. If I type Uncia and I type row number 12, with all of the columns, this is this returns that particular row for that leopard. So leopard number 12 is from Vacan. It's a male. It's 124 centimeter length. It's 37 kilograms. It has 4 ticks. That's the BCI here. So the question is, if I know BCI, if I know length, if I know the sex and the location, can I guess what number of ticks it has, right? I can do that actually by simply using that equation. So my predicted number of ticks for this particular leopard will be, so let's call this y, our prediction, equals the length is 124 times times my estimate for length, right? Length was 0.02. Right? Plus plus BCI 3, which for that leopard was that value. So I should, plus brackets times the estimate of BCI 3. Plus the sex male. So for this, I need to, how do I extract this? I need to know, so this is the expected number for females, and males have that many more ticks on average. So I need to put plus that, plus the value for males. And same for Vacan. So this is again, the intercept is for the location Altai. And Vacan has that many more ticks on average. So I simply put that. So this is simply putting these inputs, and I should extract the expected number of ticks for that particular leopard with these, because I use the values for that particular leopard as inputs. And if I run this, what do I get? I get y equals 2.7, which makes no sense, of course, because we don't want we do not want a continuous number. We want an integer, because we shouldn't have 2.7 ticks. We should have either 2 or 3. But yeah, on average, we would expect, okay, that particular bird should have around 3 ticks. And we find 4. So we made a mistake by a little bit. We didn't get 4. And this is what the residuals are, essentially. This is how much error do you make in these estimates. You have these predictions, but how correct are you? Do you make a lot of mistakes? Do you make only a few mistakes? If you make only a few mistakes, of course, your R squared is going to be very high, because you are able to make really correct predictions. There's very little error, let's say. We would expect to make a lot of error actually with this particular model, because we already know the predictors are not explaining the y variable very well, because the R square is quite low. It's only 14%. Anyway, so this is just to demonstrate what it means, these residuals. So let's extract them. We can extract them in 2 different ways. We can either fit one and extract the residuals. So that gives you all the residuals for every leopard. So for example, for number 12, we have a residual error of 0.3718. I think actually if we do, so you had 4 ticks, right? And, wait, why am I not getting the same value? So I may have made a mistake in my calculation here. Anyway, it doesn't matter. But yeah, it tells me the error. Another way to extract these residuals is to simply type resid of fit1, and I get the same values here. So number 12 is again the 0.137 and so on. Okay, so these are all my values for the residuals. So how much error did I make for each of these leopards? If I simply use the model to predict the tick number, how does it compare to the actual tick number? That's my residuals, my residual error. If I build a histogram of these residuals, so I can simply wrap this entire thing in with the hist function, I see how they distributed. And I can see that there's a bit of a right-sided skew in the residuals, which is a violation of one of the assumptions of the linear model. The residuals should be normally distributed. You shouldn't have more like error above the fitted line than below. And this is what we get here. Of course, you can see that it is still around 0, maybe slightly to the left of 0. And we can see this in our summary actually. Because, well, the median is at 0.085 actually. But the first quarter is more to the left compared to the third quarter, for example. So it's not symmetrical essentially. And we have errors that go as much as 11, which is a lot. Okay, so it's been already an hour and a half. I was not expecting to spend so much time actually on this. So Phi is asking, does this mean we don't test the data for normality before running a linear model? No, you do not. Because this is not one of the assumptions of linear modeling. At no point the assumption is that your data should be normally distributed. It is, you can look at the list. The list that I put in the last session is not exhaustive. There's other assumptions that you can add to it. The assumptions are about the residuals, the normality of the residuals, and you want the residuals to be nicely to be homogeneous as well. So the variance of the residuals should be constant as well. One way to look at that is with a plot. So if you do plot and put a model object in there, it will actually automatically return 4 different plots. So you see what happens if I do this. It says hit return to see the next plot. If I press enter, it will return the first plot. Okay, and here what do I see is that the residuals are not constant. What you want for this, and this is a diagnostic plot. This is for a fitted object, for a model, for a linear model. We see that the error, so these are the residuals on the left-hand side. Remember our histogram, it goes to a very high value here, right? So here the residual is at 11, I think, for the leopard number 43. And it goes to only -3 point something. See, this is where we see that it's not normally distributed. It's, you know, there's a lot more error in the above the fitted line than below. And what we see is that actually for very small values, the residuals are very small and they're very tight around the line. And to the more you increase these fitted values, then the error becomes even bigger. This is called heteroscedastic. I can never say that. That means your residuals are not, they don't have this constant variance. Essentially, you become even more certain at certain points. And this is another violation of assumptions. If I press enter again, I get another plot. This is to test normality of the residuals that we already kind of looked at visually with the histogram. There is some weird patterns in there, which also again suggests that, and also it seems to be kind of curved like this. So the tail that is on the left tail is kind of constantly above the line of normality and then above that line. Again, an indication that we violated that assumption. And the next plots are about kind of inferential values. This is not an assumption I listed, but one assumption actually that I didn't mention is that there shouldn't be any very influential values. So none of your leopards, none of your data points should be extremely influential. If they are, then it's going to cause issues with your analysis. So we're talking about outliers here. And if you do have very influential values, which is something you measure with Cook's distance, these plots are automatically generated. Of course, you can. There's other ways of checking model assumptions, not just these plots. But that's why they are just, it's kind of included in base R. You can look at them automatically. In the code, actually, instead of returning all 4 plots every time, I could actually, if I want, let's say just the first one, then I put which as an argument and put 1. Then it will return just that first plot we're looking at. If I was asking, okay, so is a linear model regression the same as a multiple regression analysis? A linear regression can be a multiple regression. Multiple regression just means you have multiple predictors, basically. If it's a simple linear regression or a simple regression, then it has only one predictor, one response and one predictor. In a multiple regression, we have a single response, but several predictors to explain that response. Okay, the main reason that we are getting a lot of error here is because this kind of linear model is not adapted to count data. What we want to use for count data, especially when it's a Poisson process, is a GLM. It's a generalized version of an LM. So GLM stands for Generalized Linear Model. For here, we simply use a linear model. Linear model kind of expects the response to be continuous and to be continuous. and that there will be a linear relationship between the predictors and the response, which with the count data is just not going to happen. Which is why you need to specify something extra. And that's what generalized linear models do. They kind of specify how the response variable will be related to the predictors. I won't go into details on this, but it's actually pretty simple. So I'm going to fit GLM instead of a linear model. And instead of, so that's going to be called fit number 2, GLM. So it will be exactly the same here that I put in the L part. But instead of LM, it's going to be GLM. And what the GLM allows you to do is to specify the family of models that you're working with. So there's an argument here called family. And if I put Poisson, which is usually what you might be using for count data, not necessarily, there's other families that you might be better suited, because Poisson regression has other kinds of assumptions associated with it. One of them being that the data should not be over dispersed. I will not go into details about this, but just so you know, the same way there's assumptions with linear modeling, particular types of generalized linear models, and in this case Poisson, have extra assumptions associated with them, which you'll need to check eventually. The LM that we have is a special case of GLM when the family is called Gaussian. Okay, and yeah, with the link being called identity. Oops, this is not good. So if I run this, oops, identity here. If I run this, the summary, this is exactly the same as running this. LM is essentially the same as a GLM with a family Gaussian. So if I type summary of fit 2, I will get exactly the same thing. Well, at least I would hope to get the same thing because I told you it was the same thing. But yeah, in this case, we want to do Poisson instead. And you'll see that the fit is quite different. And now we have, you see, residuals that are not as, if I do now the residuals for the second fit, they are a lot more normally distributed. This is a much better fit, essentially. I can't get from the summary, I don't get an R square. You could calculate it, actually, but the summary doesn't give it to you. So you don't know exactly how much this fits your data. But what is clear is that the location backend is still very highly significant. It's actually even more significant than before. But the estimate, you'll notice, is less than before. So we have way more confidence. So the standard error should be a bit smaller now, I guess. Is it not? Where is it? The standard error was 0.5. Now it's 0.17. So this is where we get a much better, like a much lower p-value, because we're way more confident now that this estimate is not 0. It's above 0, and we are very confident that it's not 0. Before, actually, the estimate was slightly higher. It was 1 point something, not 0.8. But we were less certain how far from 0 this actually was. So anyway, these are the general steps that you should remember: is to explore your data, making sure you have control, like you have knowledge about how different variables are related. You would come up with a regression that makes sense with respect to your research question. So the predictors you include in your regression should make sense, and they should reflect your research question, is what I'm trying to say. And of course, then you should check your model assumptions, because all the results you get will only be valid if the model's assumptions have not been validated. So for a Poisson model, for example, there is this very important assumptions of over dispersion, meaning that the mean of the y variable should not be should be the same as the variance in the y variable. If the mean and the variance are very different, and I can check that. Let me check this. I think I can simply do, okay, the mean of Untia Ticks is 2.4, and the variance of Untia Ticks is 5.3. And I can't remember if I need to look, maybe I need to look at the log. No, it's not the log. Maybe it is the mean. So here we can say, for example, that the variance and the mean are not equal. So maybe we do have some over dispersion, and maybe we should maybe use a different technique rather than a Poisson. And there's different types of GMs you can use that circumvent this issue of over dispersion. So yeah, another way of checking this over dispersion here is whether the deviance, whether the residual deviance is higher than the number of degrees of freedom, which it is the case here. It's about twice that amount. So yeah, maybe Poisson is actually not suitable here because of that assumption of over dispersion, that the mean should equal the variance. Anyway, this is just a quick intro of the steps that we should be making. Do you have any questions before we stop? So it's a lot to take in. There's, you can really do an entire course on just linear regressions themselves, but at least now you get an idea of what the steps you should go through and how to look at this summary. And again, just like any statistical approach that you'll have, one very important step is to check assumptions. Whether it's a t-test or whether it's a linear regression, they are assumptions that you should be familiar with, and you should know how to check for them. And if you are not meeting these assumptions, what else is available to you? In the case of a t-test, when there is this very simple assumption of your data should be normally distributed. If it's not normally distributed, there are other tests available, mostly non-parametric tests, which don't make those particular assumptions and which will allow you to draw your conclusions. Okay, then I guess that is it for now. Yeah.
Thanks, Guillaume. Thank you so much for doing this. And thanks, Aliana and Faye, for attending.
Thank you. It's been really helpful.
All right, glad it helps. And I guess this will be online as well. And
yeah, and we leave the group open. So if anyone has any questions or anything that they want to ask, you can via the group, and Guillaume and Anne will answer you guys. So it's a lot to take in. Thanks so much, Guillaume.
It's a lot.
Yeah.
It's again, there's plenty of tutorials online and lots of resources about all of these, but of course we don't have much time on our hand, and it's kind of like a general introduction of what we can do. There's these linear models, there's generalized linear models, and there's even more and more, every time as different attempts to fit your data better and better. Yes.
Maybe we'll ask you to come back for an advanced course as well. See, Aliana nodding. Aliana is one of our regulars with all our modules. So yeah, she'd be happy to have you back as well, I think.
All right, very nice. Yeah, well, maybe next year. Let's see.
Okay, yeah. We'll hold you to that, Guillaume, but thank you so much.
All right, well, it was a pleasure. Take care.
Bye.
Bye.